Welcome. In this project, we introduce Graphormer, a novel hybrid architecture that enhances graph neural networks with transformer-based global attention for image classification tasks. Image classification is fundamental across domains like robotics, autonomous driving, and security. While deep convolutional neural networks excel at local feature extraction, they often fail to capture long-range dependencies necessary for holistic scene understanding. This has led to a need for architectures that can model both local details and global context effectively. Many image classification models exist which use the following elements. CNNs, or convolutional neural networks, are excellent for capturing fine-grained local patterns but struggle with long-range spatial dependency. Transformers, in contrast, excel at modeling global context, yet lack built-in inductive biases for spatial coherence. Finally, graph convolutional networks, or GCNs, help relate local features but don't inherently model global interactions.
During our literature review, we studied three state-of-the-art hybrid/graph-based image classifiers. Greedy VIG blends CNNs with GNNs. Levitt integrates CNNs and vision transformers. VIG is a novel isotropic architecture which uses graph convolutions instead of attention. However, no existing model explicitly injects full transformer blocks into the VIG architecture. Our contribution, the Graphormer, is the first to do so, targeting a more effective fusion of spatial structure and global context. Even state-of-the-art VIG models lack explicit global attention mechanisms. While they leverage graph-based reasoning, they miss opportunities to aggregate information across distant patches, crucial for understanding complex scenes. Our goal is to combine the structured relational reasoning of GCNs with the global aggregation capacity of vision transformers by injecting transformer blocks into the VIG backbone.
Taking a look at the VIG architecture, we can see two crucial elements. The VIG backbone consists of graph convolutions and feed-forward blocks. These operate on tokenized image patches represented as nodes in a graph, learning local relationships. We modify this backbone by inserting vision transformer blocks after each FFN layer. To prevent interference during early training, the transformers are initialized as pass-through modules, zeroed weights with residual connections. This lets the graph gradually learn long-range dependencies without destabilizing training. Our models are trained and evaluated on ImageNet 1K, consisting of 1.2 million images across 1000 classes. We compare performance using top 1 and top 5 accuracy, benchmarking against the original VIG TI model pre-trained on the same dataset.
We had the original VIG tiny model as our baseline, a VIG with a single transformer at the final FFN for testing our training loops, and a VIG with the transformer after every FFN. This was our Graphormer architecture. We left only the transformer weights unfrozen for 7 epochs and continued training for several more epochs with all the weights unfrozen. Let's start with the training and evaluation loss curves. At epoch 8, we unfroze the full network, allowing all of the modules to be trained. This caused an immediate spike in both training and eval loss as the model had to adjust all parameters at once. During the frozen phase, we noticed a 0.58% increase in model performance. This suggests that the addition of attention is causing the boost, but it also may be due to added parameters from the transformers. More epochs are needed to make this conclusion. Once our weights were unfrozen, our model plateaued at roughly 55% top 1, well below the baseline. This indicates that the early training phase did not set a strong foundation. Through the course of this project, we have learned a great deal from understanding the basics of transformers to modifying state-of-the-art architectures and grafting one model on the other. We also gained knowledge on fine-tuning and the engineering challenges of setting up such a training pipeline. Future work on this project includes extended ablations, as well as adding more epochs so we can gather more valuable conclusions. We may also experiment with alternate backbones and upgrade our deployment plan. The key takeaway here is integrating vision transformer blocks into the VIG model results in a preliminary improvement, but we will still need to work on additional ablations and experiments to verify this. We would like to thank the EC cluster team and PSC for their support on their project. Thank you.